I'm going to be talking about receiver antennas, and I think that doing individual calibrations and providing individual calibrations are important for receiver antennas as they are for satellite antennas. This is our antenna calibration facility at Geoscience Australia. On the left we have the Geo++ robot, which we've been operating for 4 years, and on the right we have a KUKA robot, which is basically an industrial robot used for car manufacturing. We've just recently made a little bit of progress on that. I'll touch on that a little bit later on. So what I wanted to focus on today was the general assumption that we do in RGS is that we're assuming that the type mean we provide for the type mean we provide for different antenna types is representative of every individual antenna out there. And I think we're at the point where we've been doing this for about 10 years that we can no longer sustain a type mean. I think we need to move to individual calibrations. So when we try and produce a type mean, we basically try to assume that we have a minimum of 5 antennas to produce that. And that subsample is going to be representative of that particular manufacturer for the full time span of that manufacturing lifespan. So I don't think that's realistic. What you also see when you calibrate these things, when you've been working with the antenna calibration facility for a number of years, is that there is significant variation in your calibration results. So we've had to go back and carefully check our results and make sure nothing's happened with the robot and the setup just because we've seen a difference in the type mean. And really, it's just to do with the individual type variation. If we were to try and update the type mean, which is something we experienced in the last RGS for the AOD, it gets quite messy because it has quite an impact on the reference frame. So if we try to update it to be more representative of it, then it has a big impact on how we operate right now. And I think if we move to individual calibrations, it makes an easier form of operations. But it's going to require a lot more from the antenna calibration facilities later on. So we've been operating the Geo++ robot for over 3 or 4 years. And I've done a standard calibration on one particular antenna, a reference antenna that was sent to Geo++, and we sent it to Bond to be calibrated and compared the results with. And every time we sense something would be wrong, sometimes the result is a little bit spurious, we put this result calibration onto the robot and redo it. And what we have here is an accumulation of around about 66 results, and it's the difference from our calibration from the one that was obtained in Geo++. And what you'll notice from the graph is your top is L1 and then you've got L2. You've got 0 degrees elevation on the left and 90 degrees elevation on the right, and it always comes down to basically 0 at zenith. And I've got 2 little red dots that dash across there. That's sort of like the RGS sort of values. We want to be making sure that we're intercomparable within 1 millimeter for L1 and maybe 1.5 to 2 millimeters for L2. I've left it for 1 millimeters for both. And if we do one antenna calibration, we see that it's very internally consistent. The results that we've been achieving at GA have been very repeatable. They've been, it's just been no problem. We're probably getting around about 0.1 of a millimeter difference. So if we look at that a little bit of a different way, if you split up those differences in each individual calibration and put them in a histogram and you do a nice little pretty plot, you get those histogram plots on the left. So that's the frequency of differences for elevation angle over there. And then on the right is the accumulative histograms. And everything is looking quite normal and nicely distributed. So for one antenna calibration, that's fine. If I then take a mean of the differences and work out the uncertainties, that's what we get. What we see is that we're less than 0.1, 0.2 of a millimeter difference from Geo++ over the last 3 or 4 years. And the uncertainties with elevation angle are below 0.1, 0.2 millimeters. So in the plots I'm going to show later on is I've put on a little graph below it. There's a red, yellow and green there, and they represent the standard deviations. So green is within 1 standard deviation of the difference, yellow is 2 and red is 3. And I'm going to keep those 1 millimeter error bars there as well. What I'm going to try and do is if I'm talking about one antenna, I'll just have one antenna that's been repeated. You've got a little symbol up there, it's just one antenna. If I'm talking about lots of different antennas, then I'll have multiple pictures of antennas up there as well. So I had a bit of a dilemma coming to this talk trying to decide what would convince you that we need to have individual calibrations. should I provide results that are really spurious and look really dramatic, or should I just try and provide something that is more representative of what I think is going on? So I think these results are sort of like typical of what we see at the calibration facility. We've done around about 40 Zephyr antenna calibrations, and if you look at that and we compare it with the type mean, we see that we're significantly different in L2. There seems to be a little bit of a bias, but there's quite a spread of the results that we get from the individual calibrations. It's not fitting the type mean within the expected uncertainties that we have with a robotic calibration, and it's not fitting the mean with the RGS types. So I've had comments in the past saying, well, we're just doing antenna calibrations to validate our antennas, so if it doesn't meet the calibration, the antenna's no good, you throw it out. But you've already paid the money, you don't want to throw it out, you know it's tracking very well, and I'd much rather use my individual antenna calibration result for these antennas than a biased one. Again, if you look at the histograms, you can see that it's quite a spread. They're not stacking up nicely, neatly in the middle over the RGS mean, and that's not fitting nicely. This is not limited to just the survey grade sort of antennas, so it's not just like the Zephyrs or anything like that. This happens for other choke ring antenna types as well. And recently we've noticed it happening with the AOD antenna. We've calibrated 6 AODs at Geoscience Australia, the historic ones, and Geo++ have provided us with 3 calibration results from their facility as well. And what we see is this is a difference from the latest mean that's been put into RGS 14, and there's still a significant difference here. Now, the AOD is quite a stalwart for what's being used in RGS, and we're going to have biased results in there just from the calibration values that we're getting there. So we've seen lots of different individual variation within the antenna types, but one of the other major impacts that's sort of preventing this is people comment about the near-field effect. So great, you can do an antenna calibration that's really precise, but what happens when you throw it onto a pillar or something like that? What happens to the calibration values? And it's a problem. If we take that I think I've missed a slide, I'm sorry. Okay, so if we take the AOD antenna and calibrate it twice, so you're getting sort of repeatability going through here, and then you throw on a ground reflector beneath it. So you put something that approximates like a concrete pillar. It's a little bit larger than the antenna radius, and what you see is a big jump in the bias in the antenna PCV value there. So what we wanted to look at was to see what the impact was of a non-standard radome on the calibration values there. So we threw on what we call an AUST radome, which was similar to the JPL radome, similar sort of material, but just not as wide and it's not as large as a JPL radome. And we threw that onto the robot and did the calibration again, and we get the blue line, and you get an even more of a bias from your calibration result. It's not as significant as the ground plane reflector though. So if you're on a large pillar and you're putting your antenna on there, you're just throwing out the useful antenna calibration results. They're completely biased anyway. I tried it again with a different antenna type, same sort of design, used a Trimble choke ring design and put on the same reflector. And we got a very similar sort of bias, so maybe there's something there, similar sort of effect. And then the next thing we tried to do was to see if we could start moving the antenna away from the ground plane reflector. So we had these large metal spacers that we put underneath the antenna, and that would go up by about 2 centimetres each. And we had quite a bit of fun in calibrating this at GA because we'd set it up and we'd try and guess what the pattern would be next. And we got it wrong. All of a sudden, you know, you'd see it come closer to the mean or to the distribution, but then it would flip a completely different sign. So we're kind of going, wow, this is really weird. But as generally speaking, as you got further away from the ground plane reflector, you kind of got something that was getting closer to where we should be for the calibration value. So We did the same experiment again, except for the Zephyr. Now, all the lines in the middle are different Zephyr antennas that have been calibrated, and then we've taken one and just raised it up. And you can, what I haven't been able to show very well with these graphs is that the order of magnitude is significantly more for the Zephyr antenna than the choke ring antenna. So it appears that it's, I guess you could say it's more susceptible to the near field environment than the choke ring antennas we use. So what do we do with the near field? So we could try and calibrate it. So you could try and reproduce the near field environment, how you're installing your antenna out in the field and put it onto a larger payload robot like we have here for the KUKA, and get a calibration value. So, you know, I think that would work reasonably well where you have got like a standard sort of build for your tracking network. If you've stuck to a particular concrete pillar design and you've stuck to similar materials, then you can just recreate that environment on the robot and try and calibrate it with different antennas. But I don't know if it's a long-term solution for us. So we've got to decide what we're going to do with the near field. And I don't think we can just expect we can reproduce these environments and get them calibrated for everything in the RGS tracking network. We need to start moving away and thinking that we need to produce recommendations about how we set up these sites so that we can minimize the near field impact and be able to reproduce the calibration results we're getting from the robots or eventually from the anechoic chambers. So while the individual effects are of second order to near field, I still think it's very important that we move forward and start looking at trying to implement this in the antenna working group. So I'd like to propose that we start preparing for the application of individual calibrations in the RGS. So I'd like to see if the different analysis centres would be capable of applying individual calibrations in time for a next reprocessing run later on if we decide to go that way. But I think it would be very valid if we're going to install a new station or a new antenna on site that they make sure that they have an individual calibration publicly available, ready to be consumed by analysis centres for the processing. And I think we need to start accumulating our own RGS individual antenna calibration file. So not just the Antex one, but an individual one that accumulates the results from EPN and from all the other calibration facilities. But if we are going to do that, we also need to be mindful that if we're going to change our antennas, as you've seen with the AOD antennas, they're not fitting the type mean. So if we're going to remove these antennas, let's try and remove them before they're dead so we can calibrate them and see what their real values are so we don't lose that information. Now that might have an impact on the reference frame, but it'd be better if we have that information now before we lose it forever. If we're going to go into individual calibration things, we need to start doing intercomparisons between the different antenna calibration facilities, and this should be done within, you know, at least a couple of times a year. Send some reference antennas around and make sure that everyone is still producing the same results and that we can have confidence in the results that are coming from every single calibration facility. And presenting at the RGS workshop on the results would be a good thing. I think that covers what I wanted to say.